So, number 14 says that the base of a triangle is decreasing at a constant rate of 0.2 centimeters per second, and the height is increasing at 0.1 centimeters per second if the area is increasing. So I'm just going to do a little drawing here. I know it's tempting to do like a right triangle, but we don't know that it's a right triangle, so I'm going to draw something that's not. It's kind of like an equilateral, I guess. There's my height. There's my base. What formula that has to do with triangles do we know that tells us the area? Area is 1/2 base times height. Okay. So we have, based on this, we have the base could be a measurement, the height could be a measurement. Then we have the rate of change of the base, so dB dt, and then dH dt. Okay. And then we also have dA dt. Okay. So if we read the problem again, are we comfortable with how I came up with all the information I've written down so far? So I have a picture of a triangle. I've labeled the base and the height because that's what they referenced. I made sure that I didn't draw a right triangle because they said nothing about it being the right triangle. So this way I'm not tempted to use the Pythagorean theorem or something like that. I wrote down my formula for area. I wrote down my variables and I wrote down them with their rates, their derivatives with their rates of change in relationship to time. So now I'm going to go through and I'm going to put my numbers that I can read from the problem. So it says the base of the triangle is decreasing at a constant rate of 0.2 centimeters per second. So is that B or dB dt? dB dt, and that's a negative, because it's decreasing, so negative 0.2 centimeters per second. Okay. The height is increasing at 0.1 centimeters per second, so is that H or dH dt? That is dH dt, and that's positive. It's increasing 0.1 centimeter per second. Okay. Then it says if the area is increasing, does it tell us what the number is for the area? But we know that it's dA dt because it says the area is increasing. So I don't know what this is, but I do know that it's a positive value because it is increasing. So this number is a positive value. Which answer best describes the constraints on the height at the instant when the base is 3 centimeters? Okay, so I don't know this number, but I'm not solving for it. I do know it has to be positive. Does that make sense? Okay, so let's go ahead and work with the formula now. So now we're going to go ahead and take our derivative. So what's the derivative of A? Okay, so we have dA dt. And then how do I do the derivative of the right side? Product rule. Okay, so I'm going to do you guys want to do the 1/2 in the front and then do the product of B times H? Or do you want to think of the 1/2 as being a part of the B? A part of the B? Okay, so we're going to do first, we'll think of it this way, first and the second. So first times the derivative of the second, dH dt. plus the second times the derivative of the first. What's the derivative of the first? 1/2 dB dt. Okay. So let's go ahead and plug in everything we have. So we have 1/2 times 3 times 0.1. Are you guys okay with me turning this into maybe fractions instead of decimals? So 0.1 is 1/10 plus h times 1/2 times negative 2/10. Are we cool with that so far? Okay. So let's go ahead, let's clean this up as much as we can. So what is this fraction when we multiply it all out? Okay. So we have 3/20 plus, what is this? So the 2 and the 2 cancel, negative 1/10 h. dA dt. Okay, what did we know about dA dt? It equals positive. So this is positive. Does that make sense? That has to equal positive. So this value right here has to be greater than 0. It has to be positive. Are we comfortable with that? So we have an inequality. This is greater than 0. So what should we do now with that inequality? Because we can solve it now. I'm going to kind of ignore this. I'm going to work with the inequality. What should I do? Okay, so negative 1/10 h is greater than negative 3/20. I don't have to flip my inequality to do that because I subtracted a number over. I didn't divide or multiply. What do I do now? Okay. What happens when I multiply by a negative? So h is less than, and then what's going to happen over here? Negative 3/20 times negative 10/1. It's positive 3/2. So h is less than positive 3/2. Is our answer. Does that make sense? Okay. So I can see how the problem was intimidating because of the answer choices. The answer choices were intimidating, right? But if you look at the beginning of the problem, do you see how the setup actually wasn't very intimidating? The setup was kind of like the rest of the problems. Do you guys see that? When did the problem get weird? When you had two unknowns. dA dt was unknown, right? We had to go with it was positive. I think it got weird when we had to write the inequality. I think that's when it got weird. But I think we could have done most of it. So if this had been a problem where we were doing this multiple choice on our own, I think that I would have been intimidated by the multiple choice, but I think this is maybe a lesson that we should not be deterred by the multiple choice answer, because we probably could have done all of this and then maybe plugged in numbers from the answer choices to figure it out. Does that make sense? So don't be deterred, because I think that you could have done most of this problem. Uh-huh. Uh-huh. Yeah, I wouldn't have thought of that, and then the answer choices kind of give you the idea to do an inequality. Yeah. Okay. And now you've seen one like that, so now that's in your like toolkit. Yeah. Okay. Ready to do the FRQ. Okay. So this is one of those. Okay, so this is one of those cone ones. Do you still have your notes from the cone? Let's get the cone notes out, because I think that's going to be helpful. We changed our colors. The changing of the colors is the key. Say it again. Yeah, get rid of that R. Yeah.
So it makes sense for me, at least, like triangle ones that kind of have their similar steps. There's a lot of like find the formula and make a derivative of it. The other ones, however, and even some of the triangle ones, like for number 9 with the hypotenuse leg as a derivative of 0, it makes sense by how you did the other problems, but I couldn't like put together how that physically could be a slope of 0 if it was a decreasing line.
It wasn't a slope of 0, it was a rate of change of 0 because the ladder wasn't increasing or decreasing.
Oh, so all of these like rate of changes, they're not the same as derivative?
So derivative, it's saying how that length is changing in relationship to time. So that one was talking about a ladder that was like sliding down a wall. So as it slides down the wall, the length of like where the ladder is on the wall is decreasing, right? And then how far out it is on the pavement on the ground, that's increasing for that side of the triangle. But the length of the hypotenuse of the triangle isn't changing because the ladder is just the length of a ladder. So if you're saying what's the length of that side of the triangle in relationship to time, that side of the triangle is not changing lengths. So its rate of change is 0 because it's not changing. So the length against the wall is shortening, the length against the ground is lengthening. As the ladder slides down, it's getting longer, but the ladder itself is not changing. It's changing positions, but it's not changing length. That's why its rate of change is 0.
So we learned derivatives as slope, but they can also be used for rate of change?
So yeah, so they are an instantaneous rate of change. So they were talking about slope, but we're taking it into a different context now. So we're saying it's not always talking about maybe like the literal slope. So in that case, we were using the slope to represent change in y over change in x, but y, the units of y don't have to be a vertical distance. The units of y could be, in that case, the units of y would be the length of the wall over the length of the ground. Does that make sense? Or the units of y could be minutes versus seconds, or it could be length of hair versus a color or something. Like it could be, it doesn't have to be like slope as in like the slope of a mountain. It could be, so your slope, your rate of change could be all sorts of different things that don't actually look like a slope. Does that make sense?
Yeah.
So rate of change becomes a lot more abstract. And so here they're talking about the rate of change, like the slope here, the change here would be the length of something as opposed to its actual angle. Does that make sense? Something might not be changing.
Okay. Because I ended up like using the pattern of whichever one doesn't have some rate of change, 0, but I didn't understand.
Yeah, like if you were talking about rate of change of heights of people, you would talk like little kids would have positive rates of change, right? Because they're getting taller. People in the or like mid-range of life would probably not have a rate of change. They'd probably be pretty neutral. They're going to stay about the same height. Older people would probably have a negative rate of change because they tend to settle, right? Like they tend to get more souped. So their height would be shrinking. So you'd have little kids with a positive rate of change, regular, middle-aged people with a neutral, no rate of change, and then older people with a negative rate of change because they are like they're everything a little bit. So, but there you're not talking about a slope. You're not talking about like the angle of the people as it is overrun, but you're noticing the rate of change in height. So that would be comparing like their height in relationship to age. So the output would be the y, so that would be their age. The input would be their age. The x would be how old they are. Does that make sense?
Yeah.
So it's not always a literal slope. Sometimes the rate of change can be different units. So we're thinking of slope as in y divided by x, whatever that unit happens to be. But it doesn't always look like this. Does that make sense? Uh-huh. All right, let's go ahead and do the FRQ. Did you guys find your notes? All right, now what we've noticed is they used to kind of say, one in my master's program had said, you know, when you teach calculus, make sure your students can definitely do related rates because they are for sure on the AP exam, like as an FRQ. I have not noticed that for BC. So I think it might be something where it used to be very common to be on the AB exam as an FRQ, but I have not noticed that it is very common to be an FRQ for the BC exam. It seems that sometimes for maybe a part of a question, it might be FRQ, but maybe not. It's hit or miss. So you might have one, you might not. It's not guaranteed. I have noted that there are definitely parts of multiple choice problems. So you'll definitely see it on the exam. Whether or not the whole FRQ will be devoted to it is anyone's guess. You might see it, you might not. All right, so let's go look at this one. I think that the parts of the that we can definitely get are the first two. I think the other one is when things get a bit weird because it deals with surface area. I didn't really do that. Okay, so let's look at the first ones. Let's look at our notes, see if we can walk through this. Because I think that part is definitely within our reach. So we've got volume is 1/3 pi r squared h. And then let's look at the information in the problem and see what we need to do. So it looks like they told us that the overall diameter of the cone was 10, the overall height of the cone is 10. So if we have diameter is 10, height is 10. The height is changing at a rate of -3/10 centimeters per hour. Okay. The height of the container. Gotcha. So, okay, so let's just say this is like the overall height. I see what you mean. There's like height and then there's the height of the liquid. Yeah, I gotcha. Yeah, I understand what you mean. Okay, so let's go ahead and start here. So we're not even, at this point, we are not even to part A yet. Okay, we're not even on part A. So if the diameter is 10, what's the radius? Radius is 5. Okay. So look at your notes, look at the colored part of your notes. What should we do first? Okay, so what are we going to do now? We're going to cross multiply, 10R equals 5H. And what is kind of our clue that we needed to do this in the problem? What's your trigger here to like remember to do this? Yeah, they start off mentioning, they mention the diameter right in the beginning, and then after that they only talk about the h. H throughout the rest of the problem. They never mention radius again. Okay, I've seen one of these where they after that they mention both. They mention the change in the radius, the change in the height. They mention both, and you can actually do the problem in terms of both, and you do like a product rule. So if they do continue to mention both, but typically they don't. Typically they mention the radius once to kind of give you enough to do this proportion. And then after that, they only mention the height. That's very common for these problems. And if that's what you see, then you do this proportion. You get it in terms of one variable. Okay? All right, so what do I do now? So take your formula, plug in the 1/2 h. And I'm thankful this time that our fraction here is nice, because if you guys remember the last time that we did one, or those notes, that fraction was really messy last time. Okay, so if we simplify that, you don't want to just plug 5 in because the 5 is not constant. The 5 changes depending on what the height is. So because it's not a cylinder, it's a cone. And so this is us saying that no matter what the height is, that radius is 1/2 of the height. So we're allowing it to change. Okay, so there's our new formula. Are we good? Okay. So now let's go ahead and go to part A. We have our new formula. Now we're saying that the height of the liquid is 5 centimeters. Now we can use our dH dt as -3/10. So the height of the cone itself was 10, but the height of the liquid is 5. The depth of the liquid is 5. All right, what do we do?
Oh, you find the derivative.
Yeah, let's find the derivative. So dv dt equals what? So what do we do? Plug in the numbers. So we got 1/4 times pi times 5 centimeters squared times -3 centimeters per hour. I love when you plug the units in and they work out. The one that I cannot make sense of the units on are the angle ones, where somehow the units output. How can you input something and output radians from nowhere? no sense. Those like really mess with my brain. I don't. Okay, so 25 times 3, 75, so negative 5 pi, right? 40? Is that right? We can divide by 5 centimeters cubed per hour. Okay, divide by 5 is 15. Divide by 5 is 8. Okay. What?
The A, but the rate of change stuff that we're doing right now, I did that for A, do we have to find rate of change, or is it just, I just wanted to find for the volume.
Oh, I am looking at, this is B. What is, oh, it just says find the volume of the container when H equals 5. Yeah, label, this is B. I'm so sorry. This is me just like going straight through and doing related rates because that's what I'm used to. Sorry, this is good. Madeline, you were right. You're right. I heard somebody say ask. Ask. Is just 1/12 pi h to the third, which would be 5 to the third. I'm so sorry. 5 to the third is 125. There's A. That one's easy. That's CM, not OM. We're doing yoga all of a sudden. Gosh, am I one of those teachers who's culturally offensive? Have you guys seen that TikTok going around of the teacher doing the Sokotoa thing? Oh my gosh, I cringed so hard when I saw that. Her is so bad. She put colorful pants on and a headdress, and then she just ran around the room saying Sokotoa, and I just wanted to stab her in her white face because it is so bad. She just made a fool of herself, and then Sokotoa is gibberish. It's not even native. People were like, she needs sensitivity training, and I was like, no, she needs to be fired. That's not her trying to make a math lesson interesting. That's her mocking somebody's culture. So, for a math lesson. Fire her. Oh man. A native person, and he was sitting there, and it was like playing in the background. And he was just like stone faced. And then he said at the end, "That's a great way to phrase it." Yes. Yeah, the kids were like awkwardly silent at first. There was some laughing, but it was mostly awkward. You guys, if I ever do that, somebody stand up and slap me. Like, you have my permission to just stand up and slap me. We got A, we got B. How do we feel about that? Good? Okay. So, part C says, show that the rate of change of the volume of the water in the container due to evaporation is directly proportional to the exposed surface area of the water. What is the constant of proportionality? So the surface area Oh, I gotta think about this. This, let's, where did I get this formula from? So, well, okay. Can somebody Google surface area of a cone real quick? It is a circle, but I'm trying to think about why I knew that. So if you can, because what we're dealing with here, we're not doing the entire surface area of a cone because we're not doing like this base part, right? So this part would be like one area of a circle, but like the other part right there, if you were to put a slit down the side and like lay it out, that's also the area of a circle. Can you guys picture that? So the base is a circle, right? So that would be the area of one circle. But if you did a slit down this side, that's another circle. I gotta think about. Yeah, I'm just trying to. Yeah. Oh, you didn't think about the base as being part of it? Well, the formula that Josh read, I'm pretty sure included both. Is just what I was clarifying. You were just thinking of the cutting open the.
Well, yeah, for this specific, or at least for like this one that we did.
Uh huh.
I thought it was just like for unraveled into the circle.
Yeah. Okay. This is where headache Miss Rice is not helping because so I have written surface area equals pi r squared. Which isn't making a lot of sense to me at the moment. No, because you work with that to get the rest of it. So there's a relationship between like the way that derivatives work. So you know how like if you wanted, like if you took the derivative of a cubic function, you'd get a parabola. If you take the derivative of a parabola, you get a linear function. Your units of measurement work the same way. So if you take the derivative of a volume, you get an area. If you take the derivative of an area, you get a length. Does that make sense? So I think that's kind of like the idea that we're going with here is that we're showing that. So for your surface area, we're just going to start here. Surface area starts with the area of a circle, which you guys can kind of see from that cone. And then if we start with this, we're going to say pi. And then remember with the r, we replaced r with 1/2 h. And that was from earlier on the problem. We did our proportion. We said that r was equivalent to 1/2 h. So this is saying that pi is 1/4. It's pi times 1 h squared. And so the surface area is 1/4 pi h squared. And so if you flip the exact same thing at dv dt, it's 1/4 pi h squared times dt. Does that make sense? dv dt is 1/4 pi h squared times dh. And so that means that the constant proportionality is dh dt, because this is the number that is multiplied by this. It's the number So what it means is if something is directly proportional like that, it means that if because when you can see in the cone that the higher, the like deeper the water is, the more surface area is exposed, right? So they're just saying that the more, like the deeper it is, the more exposure there is, and so the higher, like the bigger the surface area of the water is, so the more evaporation you're gonna have. So if there's more water, if it's deeper, more surface area is showing. So they're directly proportional. That's what they're saying. And the constant of proportionality is that -3/10. And basically the reason is because volume and surface area are directly related, and they're directly related by the derivative. Because the derivative of centimeters cubed is centimeters squared. We notice there's that direct relationship because the derivative, if you take a cubic, that derivative is a parabola whose derivative is x, right? X cubed goes to x squared goes to x. When you take your derivatives, they always drop the exponent by 1. And that relationship holds true when you're doing these application problems too, that if you start with a volume, the derivative of a volume goes to an area because it goes from x cubed to x squared. And then the derivative of an area goes to a length. So they're saying here is that if you have that overall volume of water, right, that there's a direct correlation between how deep that water is in the cone and the surface area that's exposed. So the deeper the water in the deeper that water is in the cone, the more the water of the surface is that's showing, right? So here's how much surface water you have showing, right? If I made that a little bit deeper, there'd be a little bit more surface showing. And then that is making a difference to how much evaporation is happening. Like if you have more water on the surface, then you're going to have more evaporation. Does that make sense? Because you have more water showing. So they're saying they're directly proportional to each other. If I have more surface water, I'm going to have more evaporation. If I have less surface water, I'm going to have less evaporation. So there's a direct correlation there. They're just saying, so you know how when you take the derivative of something, if it has a coefficient, that coefficient just hangs out in the front? That's what we're picking out. Because we're saying, oh, that coefficient hangs out in tenths. So that is the relationship it's just chilling there. That negative 3/10 must have been the coefficient, and it's chilling in the front, and so that is the relationship between them. So there was a negative 3/10 in front of the x to the third for volume, and then there was a negative 3/10 when they took the derivative, and it became an x squared for area. That negative 3/10 was still hanging out in the front, and so that's the proportionality. So that negative 3/10 was that. So if you're thinking in terms of the algebra, that negative 3/10 was a coefficient that was just chilling in the front. And so it made a difference for the volume, and it made a difference for the area too. The negative 3/10. It stayed the same. It was in both problems. Yeah. So we're noticing it, and that's the algebra behind it, is that coefficients, they get to stick in the front. That when we take the derivative, they just get multiplied by that exponent. So we see them just trailing through the problems. We see those constants, or those coefficients in the front, we see those coming through the problems. So algebraically, it makes sense because we've always done that. Right? We've always had those coefficients just get multiplied through. So we've experienced that before. And then you take the rest of the problem and you just do the derivative with the rest of it. So that's what we're showing, is that, like, oh, when you have the surface area, like, yeah, they just took the derivative and then there it is. That's the derivative of the volume, so that's exactly what we expected, is they just dropped the exponent by 1. Mm-hmm. Yeah. Yeah. And then the coefficient was just still there, and the coefficient was the negative 3/10. So that's what makes it directly proportional. And then you can see it in the picture too, right? Because depth has a direct relation to surface area is so if you have more surface area, less deep, you're going to have less surface area. So that makes sense as well. It's kind of intuitive. Yeah.